Let's try to solve this example. Okay, please make a pause of this video and then carefully read this example statement and think about how you want to tackle this question. Okay, now let's try to do it together. So we have a Carnot cycle, and that has air with a mass of 0.6 kilogram inside, and the temperature limit of this cycle is 300 Kelvin and 1200 Kelvin. And also the minimum and maximum pressures also are given as 20 kilopascal and 4000 kilopascal. Now let's assume that this air, ideal gas, has constant specificities, and we are given Cp value and Cv value. And from those given values, we also can calculate the gas constant, which is 0.287 kilojoule per kilogram Kelvin, and the specific ratio is Cp divided by Cv, 1.4. Now I want to calculate the net work output per cycle. Before we go further, let me correct the answers. That is 92.16 kilojoule. Now, the first thing that we want to do always for the thermodynamic cycle analysis is to try to draw TS diagram and PV diagram. Okay. Can you draw the TS diagram and PV diagram of the Carnot cycle? Let's try to draw TS diagram first. And in the TS diagram, the Carnot cycle makes a rectangle, okay, between TH and TL. Now we know this TH is 1200 Kelvin and TL is 300 Kelvin. Also, that is bounded by S1 and S2. Now, if we try to draw PV diagram, we can draw this way. So we have 1, 2, 2. We have 1, 2, 3, and 4, and 1. Now we have 1 to 2, 2 to 3, and 3 to 4, and 4 to 1 of the Carnot cycle in PV diagram. And from the given PV diagram, now we know P1, okay, and P3 as the maximum and minimum pressure. So in the case, P1 is 4,000 kilopascal, and P3 is given as 20 kilopascal. Okay. Now, how can we calculate the net work output? So now let me just write it out as net work output for the Carnot cycle. Now, in terms of graphics or on TS diagram, net work is area surrounded by the closed loop. So that is net out. Same thing in the PV diagram as well. The area inside this closed loop is your net out. So net work out of the Carnot cycle can be written as area of the rectangle, that is TH minus TL times S2 minus S1. That is same as TH minus TL times M times specific enthalpy S2 minus small enthalpy S1. Okay. Now we know TH, we know TL, and we know M, but we don't know S2 minus S1, the specific entropy change. Now, how can you calculate the specific entropy change, S1 and S2 minus S1? Because we are using ideal gas and constant Cp and Cv, S2 minus S1 can be calculated using the equation Cp natural log T 2 over T1 minus R log P2 over P1. Okay. So now when you talk about, when you just think about the change between the state 1 and state 2, so state 1 and state 2, the process is isothermal process. So this term is gone because T1 same as T2. Now we know P1, but we don't know this P2. Okay, then how can you calculate this P2? Okay, so now in order to calculate this P2, we have to, let me just focus on what happens during the process 2 to 3. We know the pressure at 3, but we don't know the P2. But what we do know is the process between 2 and 3 is isentropic process. So now let me write it down. So from 2 to 3, process 2 to 3 is basically isentropic process. And when you know the ideal gas and for constant specific heat, we have equations that we can use for the isentropic process. I hope that you remember those equations. Okay, so for that case, isentropic process equation is P V part by K is constant, or T V part by K minus 1 is constant, or we have T P part by 1 minus K divided by K is constant. Those three equations are essentially the same but with different variables. Now, among these three equations, let me use that equation because that directly gives us the relation between temperature and pressure. So in that case, we can write it down as T2 over T3 is equal to P2 over P3 part by K minus 1 divided by K. So from this relation, what we do know is P2, which is now T2 is TH and T3 is TL. So what we have is TH divided by TL. Now powered by K over K minus 1 times P3. And then if you apply all values here, that gives us 2560 kilopascal. So, okay, let me just... So from those values, what you know is S2 minus S1, which is minus R natural log P2 or P1. And now we do know everything, so it gives us 0.128 kilojoule per kilogram Kelvin. So now net work out is TH again my TL times M times S2 minus S1. Then by applying all the numbers, then it gives us 92.16 kilojoule. Okay,